This lecture will cover section 5.5 out of the book, and in particular the section on Markov chains. So first, a definition. A Markov chain is a process that consists of a finite number of states and known probabilities, Pij, where Pij is the probability of moving from state j to state I. So that's the definition, but we've actually seen a couple of Markov chains already. So we'll see some examples in a minute. For a Markov chain, we're going to specify the states and a transition vector for each state. And you're going to see these are going to look very familiar. We're just going to write them down a slightly different way. So as an example, everyone lives in a city or not in a city. For everyone that lives in a city, there's an 80% chance they still live in a city in a year, 20% chance they do not. For non-city persons, there's 40% chance they move to a city. So this is very similar to some of the problems we've already done with transitions. So we're going to write that down just slightly differently. This time, we're going to define two states. State 1 is that somebody lives in a city, and state 2 is that somebody lives in the suburbs. And for each state, we define a transition vector. So this is the same as building the matrix that we built for these similar problems. So we build a transition matrix for each state. So for state 1, living in a city, P11 is the probability that you go from state 1 to state 1. In other words, that you stay in a city. P21 is the probability that somebody goes from state 1 to state 2. So lives in a city and transitions to living in a suburb. And you can see the vector that you get from it from the numbers we were given. A2 is suburbs or non-city. So P12 is the probability that someone starts in the suburb or starts outside a city and transitions into a city. P22 is that you start outside a city and your transition is that you stay in the city. Combine them into your transition matrix, and that should look familiar to you. Now, here's one slight difference with Markov chains. With Markov chains, not always, but normally we talk about things in terms of percentages, the percentage of things that are in a certain state. So whereas before we would talk about having 500,000 people in a city, now we're going to talk about, in Markov chains, we generally deal with probability vectors. What's the probability of being in one of your states? So here we have two states. State 1 is in a city, state 2 is outside a city. What's the probability that somebody's in state 1? This additional information says there's a 70% chance that the person is in a city. So we write our probability vector this way, as what is the probability of being in that state. When you do that, you then calculate the probability vector for the next year, being your matrix A times your probability vector, which is what we have here, and then you calculate it, and that's the probability vector for the next state or the next step, the next after the transition, whatever it happens to be. Okay? So notice three things. The sum in every column of the transition matrix is 1. The sum of entries in the probability vector is 1. And after you multiply, the sum of entries in the transition matrix multiplied by the probability vector is 1. So your next probability vector, they also add up to 1. Okay? So when you're dealing with Markov chains, that's a normal property of what you're dealing with most of the time. Why are we introducing this as Markov chains? Well, we've talked about these transition models where you're looking at what happens 5, 6, 7 years in the future. But one of the things you often ask with Markov chains is what is the steady state vector? So you're saying, what is a vector where things stabilize? It's where things don't change from one transition to the next. The percentages don't change. You may have individuals, you will have individuals that move from the city outside the city and vice versa, but the percentage doesn't change. It remains constant. In other words, what does that mean? We're looking for a probability vector where AP is equal to P. So applying the transition doesn't change the probabilities. So in our previous example, we're looking for a vector P1, P2 that has that relationship, where multiplying it by the matrix doesn't change it. Now that, after our last lesson, should look familiar. This is the eigenvector of your matrix that corresponds to the eigenvalue of 1. Now, in our previous one, we had to go through and we had to figure out the eigenvector, the eigenvalues first and what the eigenvalues were. Here, I'm telling you that there is going to be an eigenvalue of 1. Remember our conditions on the previous page when all the columns add up to 1? Except in very rare cases, that guarantees that you are going to have an eigenvalue of 1. So when you have a transition matrix, you are guaranteed, almost guaranteed, that you are going to have an eigenvalue of 1. So you can start by assuming that eigenvalue exists. Then we just have to calculate the eigenvector. That eigenvector is exactly the steady state vector. It's the vector that doesn't change after you multiply it by the matrix. That's the definition of an eigenvector. So for instance, here's our example. We have our matrix A for the problem that we just did. So we're looking for the eigenvalue that corresponds to it. And I miswrote this. This should be minus 0.2. That should be minus 0.4 there. Again, you work with the matrix A minus 1i for the eigenvalue of 1. When after you do this, I skipped a couple of steps here, but you end up with that as your augmented matrix. What does that tell you? Well, write out your equations and so forth. Get your basis. Once you do that, you're going to end up with the basis for your eigenspace or for your null space of the matrix. The basis for your eigenspace is generated by 2, 1. So that means any vector that's a multiple of 2, 1 has that property where A times the vector is equal to the vector again. But we also had this condition where all of the entries of the probability vector have to add up to 1. And here you don't. They add up to 3. So what do? You just take your vector and multiply it by 1 over the sum. So your probability vector times 1/3 equals that. That is a vector that is in your eigenspace. In other words, multiplying that vector by your matrix gives you the same exact vector. And you also have the property that everything adds up to 1. That is your steady state vector. So if you have it where 2/3 of your people live in the city, 1/3 of your people live outside the city, with that transition as defined, it's not going to change. You found your steady state. And in fact, what tends to happen is when, no matter where you start at, usually, you will tend to go towards this steady state. Things will tend to move towards that vector. So as another example of a Markov chain, here we're going to look at a biologist studying a breed of dog. The transitions are going to be from generation to generation. So we have a biologist that is studying dogs, noting that they only ever have blue, brown, or green eyes. If a dog has blue eyes, their offspring has 80% probability of being blue-eyed and 20% being brown. If a dog has brown eyes, then their offspring has 20, 40, and 40% chance, respectively, for the 3 colors. If a dog has green eyes, there's a 20, 10, and 70% chance their offspring have those colors of eyes. What's the steady state vector? First, define the states. Now, when doing one of these problems, I'm always going to be looking at you to write down what the states are. So the 3 states are blue eyes, brown eyes, and green eyes. Those are the 3 possibilities. Next is define the probability vectors. So for state 1 of blue eyes, what's the probabilities? 80% chance of staying with blue eyes, 20% chance of having brown eyes, or of transitioning from state 1 to state 2. If they have brown eyes, there's the probability vector for what their offspring are. If they have green eyes, again, there's the probability vector for what their offspring are, which gives us a transition matrix, which you get by just putting all 3 probability vectors together in one matrix. Now, we're looking for the steady state vector. So we're looking for the eigenvalue that corresponds, for the eigenvector that corresponds to an eigenvalue of 1. We do that by row reducing a minus I. Well, there's a minus I. Row reduce it, you get that. So I've saved you the steps in between and show you the row reduced echelon form of it. This gives you 1 free variable. So that means that the basis has 1 vector. The basis of the eigenspace is the basis of the null space for that vector, which is 7 over 4, 3 over 4, and 1. Again, normally you do that by writing down the equations, but I've just jumped to writing down the basis. So that's our eigenvector. But now they don't add up to 1, so we have to scale it. They do add up to 14 over 4, so you have to divide every entry by 14 over 4. When you do that and you simplify, you end up with that as percentages. That's your steady state vector. A times that vector equals the same vector. In other words, your probabilities of being in each state at the next step are the exact same as what you started with. So this suggests that over the long term, you end up with 50% blue eyes, 3 over 14, which is about 21.4% brown eyes, and 2 over 7, or about 28.6% green eyes. And here's some suggested practice problems for the end of that chapter. Thank you very much for your attention.